Hi there, welcome back to another video on organic chemistry. So today we are going to learn about the family called alcohols. And what makes alcohols special is they have an OH group anywhere on their molecule that gives it the alcoholic features. So let's have a look at the alcohols. Is a normal alkene or alcohol or alkane, and then with an OH group attached to it. So this OH group is the functional group that makes this alkane, turns it into an alcohol. So this alcohol is named either, so if we look at this one, it's a 3, so it's prop. And because it's an alcohol, it has a surname of anol. Okay, so propanol as alcohol, or if we have a molecule that looks like this, for instance, that has a double bond, so it's an alkene, that surname, the ene, is really taken at the end of the molecule, or at the end of the name, so we need to put this alcohol somewhere in front, so we're going to call it 1-hydroxy. Prop 1-ene. Okay, so the ene is the surname because that's the main group, alkene, and the OH is the add-on, and it's on carbon number 1. So for this one, we didn't put a number there because it is on carbon number 1, but if the OH was on this C, it will be propan 2-ol. So remember to add the number of where this OH group is on the molecule, so that we know where the OH is. Okay, so we're naming it. We either name it with an anol or ol at the end of the name with a number, or we put it in front if the surname has already been taken by another group. Okay, so this usually happens with anes, the anes is going to be, so enes, amines, stuff like that you might want to go and put it in front. So both of them are right. Yes. Okay, so we know now how to name it. Now we need to have a look at some of the properties. So the two properties that we're looking at is melting and boiling points and solubility. So first of all, when you look at a molecule, so let's say it's propan 1-ol. This molecule, let's have a look at solubility first of all. Solubility is based on polarity. So when you look at this molecule, do you think this is going to be a polar or non-polar molecule? And when you look at this, we can kind of see that the O is more electronegative, which means that electrons will be drawn towards the O, which means that that part is going to be negative and this part of the molecule is going to be positive. So alcohols are soluble in water. The trick to this now is if we have a molecule that looks like this compared to a molecule that looks like this, the size does matter in this case, because when you look at this, there's a definite positive and negative side to this molecule. So it gives it a strong polar charge, positive and negative. But when we look at a molecule that this is this size, although this one is more electronegative, it won't really have an effect on this electrons on this side of the molecule, which means that this part is not going to be very positively charged compared to this negative. So as the molecule increases in size, it loses its solubility. So the bigger the molecule, the less soluble it is in water. Okay, so solubility. When we look at melting and boiling points, we look at the forces between these molecules. So when we look at a molecule that looks like this compared to a molecule that looks like that, the melting point will be higher with this one compared to that one. Because when we look at melting and boiling points, it's these forces between these molecules that need to be broken. So if this is another molecule that's this size, all this surface area is going to hold the molecules together. And if it's a small molecule, this surface area is much smaller, which means that the melting and boiling points will be lower. This one in comparison is much larger, so it has a larger surface area to hold the molecules together. So melting and boiling points increase as size increases, but solubility decrease as size increases. Okay, so those are the two things that we need to look for. We know how to name them: melting and boiling points and solubility. Now we're going to look at classifying organic alcohols. So classifying alcohols. So you can get primary, secondary, and tertiary alcohols, and it all depends on the carbons that this OH is bonded to. So when we look at a molecule that looks like this, we are going to focus on the carbon that's attached to the OH. So this is the main thing that we're going to look at. And this carbon that's attached to the OH is only attached to one other carbon. And because this carbon that's holding onto the OH is also holding onto one other C, we call this a primary alcohol. When we look at a molecule that looks like this, and we have a OH on this side, again we're going to focus on the C that is holding onto the OH, and now we can see it's holding onto one C and it's holding onto another C. So this C that's holding onto the OH is connected to two C's, and guess what it's called? It's called secondary. Okay, and I think you can guess what the third one is. So when we look at this carbon holding onto the OH, so we're focusing on this carbon is holding onto 1, 2, and 3 other C's. So this then is called tertiary. Okay. So this classifying method can be used with haloalkanes as well. So they can ask you, and as a standalone question in the exam, classify these alcohols or haloalkanes as primary, secondary, and tertiary, and you will need to know how to classify and even describe how you got to your answer. Okay, so classifying alcohols. Primary, we're focusing on the C that's holding the OH. If the C is holding onto one other C, it's called primary. If it's holding onto two other C's, it's called secondary. And if it's holding onto 3 C's, it's called tertiary. Okay, so important classifying alcohols. Now we're going to go into our reactions, and there are quite a few reactions with alcohols. So the first thing that we need to know is if we look at, so we'll go reactions. So the first one, if we have an alkene and we're adding water to it, put another C there. What's going to happen is, remember with the H2O, we're adding H's and OH's. So one of these arms will open up and grab onto the H, another of these arms will open and grab onto the OH. So what we have here is a molecule that either has an OH and an H on that side, or it could be a molecule that has an OH and an H. And remember Markovnikov's rule, the rich gets richer. So it follows these are the two potential products. And when we follow the Markovnikov's rule, the major product is going to be the molecule or the product that's followed this rich gets richer rule. So this one had 2 H's to start with. This one only had 1 H. If the richer one gets another H, we call that a major product. And that one is a minor product. And remember, this only happens when a molecule is asymmetrical, when there's 2 options, we follow Markovnikov's rule. Okay, so the first one, reaction, is we've got an alkene, we're adding water to it to form an alcohol at the end. This is called an addition reaction because we're adding molecules to little parts or atoms to the molecule, so called an addition reaction. The next reaction that we'll be looking at is, again, if we have an alkene, but we oxidize it. And when we oxidize it, it forms a diol. So those two arms are going to open up, and each of them will be added to an OH. So this is called propane 1,2 diol. Okay, so that means two OHs. Okay, the next one, let's quickly whip through them. We've got a haloalkane, so we might have one bromopropane, and when we add potassium hydroxide in aqueous, remember it's not strong enough to take both an H and a Br, but because it's aqueous, it can swap, it sends in its wingman, and then the Br gets substituted with the OH, and then we have KBr at the end. Okay, going home. So this again, because we're swapping it, is called a substitution reaction. So addition, oxidation, substitution. Then we have an alcohol. If we start with an alcohol, and we adding hydrogen halide, like hydrogen bromide or hydrogen iodide or hydrogen chloride, whatever, what's going to happen is the OH will be swapped with the Br, so we're making a haloalkane, and then what's left is this H and this OH, and it's going to form water. Again, a swapping reaction is called a substitution reaction, and then based on that, for the next one, is we still have an alcohol, but if we want to go out and we want to add Cls, we have three options, or three carriers of Cls. So we call it, I call it Sockle or Mypockles. PCl3, PCl5. So Sockle and Pockles, any of these three, if I add those, the Cls will get swapped with the OHs. So in this case, we have a chloropropane that forms. Okay, so Sockle and Pockles are the carriers of Cl. So if we want to add Cl, we always use Sockles and Pockles. Right, so the next one, if we have an alcohol, and we oxidize it, remember oxidation with MnO4, what's going to happen, and this is where wine turns into vinegar. So we have an alcohol, and we leave the wine too long in the fridge, and we go and drink it again, it becomes sour and not very nice, because it's turned into an acid, a carboxylic acid. So this is turned into vinegar, for instance. Okay, so alcohol, if we oxidize it, it becomes a carboxylic acid. The problem is, or the trick with this, is only if a molecule has an OH at the end, will it form a carboxylic acid. If it's in the middle, like, it won't get oxidized at level 2 yet. At level 3, you'll see there is another product that forms, but you don't need to know it for now. And then the last one, if we've got an alcohol and we want to remove the alcohol, so we want to remove water, we add H2SO4, that is concentrated. And when we do that, we take the H and the OH away, which means that we have a double bond at the end. But remember, if this OH was in the middle and it's an asymmetrical molecule, we again have two options, like major and minor, because we're using Zaitsev's rule that says the pore gets poorer. So the H with the C with the least amount of H's will lose another H, so the double bond will either be on this side or on that side, depending on where the porous C is. Okay, so let's quickly recap these reactions. We have an alkene, we're adding water to it, an addition reaction, and we're forming major or minor products if it's an asymmetrical molecule, and we're forming alcohols. We can also have an alkene and we oxidize it to form a double alcohol called a diol. If we have a haloalkane, we can swap the halogen with an OH to make it an alcohol, and that is with a weak or dilute KOH, aqueous. If we have an alcohol and we add a hydrogen halide, so hydrogen with a halogen, we can swap the OH with the halogen to make a haloalkane. So that's again a substitution reaction. Again, we can substitute it if we specifically want to add a Cl to it. We swap it with PCl or socols or pocols. If we have an alcohol and we oxidize it, again wine into vinegar, we're oxidizing it and it becomes a carboxylic acid. And then the last one is if we have an alcohol and we add concentrated sulfuric acid. Remember, concentrated sulfuric acid draws out water in any of the reactions that we add it to. So it takes anything that makes up water, H's and OH's, and because there's no OH's and H's left, these two arms will close up to form an alkene. Quick summary of alcohols. This is pretty much all you need to know about alcohols. The properties, how to name them, primary, secondary and tertiary, and then all these reactions. Okay, so see you later. Chemistry, baby,